Hi guys, and welcome back to my channel. In this video we'll be going over the SChO silver problem 1, so the silver tier first problem. So this was sort of like an intro organic question, and I think it was a good sort of first problem for silver tier. It wasn't super difficult, it was more just a review of your knowledge. So if you knew all the reactions, like if you read through a book like Klein's Organic Chemistry and you had a solid sort of understanding and a solid knowledge of all the basic reactions in organic chemistry, you would sort of be in pretty good shape for this problem. So let's just go over it now. Basically, we're talking about synthesizing the active substance in the drug Viagra. So let's just start with the synthesis. So we start with phenol and the pyrazole derivative shown below. So if we look at question 1.1, we're basically asked the structures of A, B, and C. So we can see that this is, we just need to look at the reagents and see if we can come up with the structures. So let's do that. You can see we start with phenol here. This is phenol. And what are we applying to phenol? What are our reagents? In our first step, in our first step, we have NaOH and we have CO2. So we want to note what exactly our reagents are, right? We want to sort of understand what their purpose is. So NaOH is sodium hydroxide. It's a strong base. So we want to look at, okay, this is a base. So what can bases do? It can deprotonate something. It can deprotonate an acid, right? So we want to look for acidic protons and see if the base can deprotonate it, right? What is CO2? CO2 is what we call a Lewis acid. And why is it a Lewis acid? Basically, the carbon in CO2, if I draw it out here, we have very electrophilic carbon because both the oxygens are sort of drawing electron density away from the carbon. So there's really low electron density at the carbon, and so it's a really good electrophile. It wants electrons. So yeah, carbon dioxide is a Lewis acid. So now let's think, right? So we have our phenol. We're first deprotonating something with our NaOH. What can be deprotonated? Our alcohol proton. Phenol is pretty acidic, relatively acidic. So we deprotonate our alcohol proton and we get something that looks like this, right? And now you can see what this sort of oxygen group here can do is it can donate these electrons into the ring. So we can have resonance that looks like this, right? I can push these electrons around the ring, and so we can get something like this, right? And we have all these resonance structures that we can draw. There's obviously you can push the electrons around the ring, but basically what we call this sort of oxygen group, this is an electron donating group. It's donating electrons into the ring. So the ring becomes, so aromatic ring becomes a better nucleophile. Why? Because now there's higher electron density in the ring because we have this donating group of electron donating group that donates this electron density into the ring. So there's more electrons, which means it's more nucleophilic. So what can this do? Now this can these electrons can now, it's a nucleophile, right? And we said that carbon dioxide is a good electrophile because the carbon is very low electron density. So this can attack, right? And we can have this sort of nucleophile electrophile attack. And what does this get us? This gets us something that looks like this. So we would have basically a carboxylate group. Now we have a carboxylate group here. Okay. And then what happens is some base will come along, and because aromatic structures are so stable, this base is just going to deprotonate this hydrogen, and we're just going to regenerate our aromaticity, right? We always want to go to become aromatic. When it's not aromatic, it's really high in energy, and bringing it back to aromaticity basically lowers the energy significantly. So we end with something that looks like this. And this reaction, this sort of idea should be familiar to you. This video is not supposed to explain all these concepts. If you read through a book like Klein's Organic Chemistry, the idea of nucleophile electrophile attacks, the idea of activating a ring, these should sort of be familiar, right? One question you might have is, why did we attack at the ortho position to the alcohol group, right? We could have attacked at the para position, because if you can see in this resonance structure, in this first structure here, we could also draw a resonance that puts the negative charge on the para position. So you might ask, why did we not attack at the para position? That's a fair question. One way to figure out why we didn't do that is if we look at the product, right? If we look at this end product all the way at the end, and you can see that we have this somewhere in our product, right? This sort of benzene ring derivative. And if we look at our product, it looks like this is where that benzene ring derivative is, right? And you can see that we have sort of our oxygen group thing that's coming there. And you can see, again, ortho to that is another group. So this should sort of give you a hint that maybe we want to attack ortho instead of para, and that's what is the correct answer. We want to attack ortho rather than para. So also this process, right, where you add NaOH and CO2 to phenol, this is called the Kolbe-Schmidt process. So if you want a name to go along with it, that's not really necessary, but this is an actual common process where it's a common way to produce salicylic acid from phenol. Okay, but that it wasn't really necessary to know the exact process. You could definitely reason this reaction out. So then we have our second step where we add acid and water. So this is basically like an acidic workup step. So we're just protonating stuff that is deprotonated, right? As you can see in our final sort of product here, we have our phenol oxygen, or our alcohol oxygen that was deprotonated. We also have our carboxylate that's deprotonated. So when we add sort of excess acid, right, what are we going to do? We're just going to protonate these deprotonated spots. And so we're going to get back our OH group, and we're also going to get a carboxylic acid group like that. So we're just protonating the stuff that we have deprotonated. So that's what A is. Our structure of A is our benzene ring, our aromatic ring with the OH group and also the carboxylic acid group. So now let's look at the second reaction to get B. We can see that first we add 2 equivalents of NaOH. And note that the number of equivalents is really important. 2 equivalents of NaOH means we're deprotonating something twice. We're deprotonating 2 acidic protons. So that's something to note. We're deprotonating 2 acidic protons, right? And if we look at our compound, we can see that we should have 2 acidic protons. We have our phenol proton, our alcohol proton, and our carboxylic acid proton. So we're basically going to deprotonate both of them. That's what we do in our first step. We basically deprotonate both of them, so we end up with that, right? Next, you can see we add 1 equivalent of ethyl iodide. So what is ethyl iodide? Ethyl iodide, can basically be used as an electrophile, right? The carbon connected to the iodine is a little bit electrophilic because the iodine withdraws electron density, and the iodine is a very, very good leaving group, right? I- is very stable. So basically what can happen is if we have ethyl, that's ethyl iodide. If we have a nucleophile, this can just attack the carbon, and in an SN2 type reaction, right, we're basically, what we're going to do is we're going to ethylate some nucleophile. We're going to add an ethyl group to the nucleophile, and the iodine leaves, right? So, but note we only have one equivalent of ethyl iodide. So we want to figure out which nucleophilic site is the strongest nucleophilic site, because the strongest nucleophilic site is going to be the first to attack the ethyl. And we don't have two equivalents, which means that both the nucleophilic sites attack, right? We only have one equivalent, so we got to pick which nucleophilic site is going to attack. So we have two negative oxygens, right? So either one of these could potentially be the nucleophilic site. There's high electron density where there's a negative oxygen. But our carboxylic acid group will not be the one to attack because we have resonance with this carboxylic acid, really good. Like the negative charge in the oxygen is sort of delocalized across both of the oxygens. Whereas the negative charge on the other oxygen, right, on this guy, is delocalized into the ring, but it's not as delocalized as with the carboxylic acid group. So basically there's a stronger electron density, higher electron density on that oxygen. So that's going to be our nucleophile. Okay, so this oxygen, right, is going to attack the ethyl iodide, and it's going to be ethylated. So we can draw this. We have our benzene ring, and this is going to form O-ethyl, and we're also going to have our same carboxylate group coming off. And then in our third step, you can see we have an acidic workup again. This is acidic workup. So it's the same sort of idea as our last step. We just want to protonate all the things that we deprotonated along the way. So our carboxylic acid group, our carboxylate group is going to get protonated. So we add acid, and we're going to end up with O-ethyl and carboxylic acid group like this. So this will be our answer for B. In our next step, we see that we have SOCl2 as our reagent, and this is a very common reagent. You'll see it pretty frequently. What is SOCl2? It basically is a chlorinating. It's chlorinating agent. So basically what it does is it'll take an alcohol group or a carboxylic acid group and turn it into either a chloride or an acid chloride group. So you can see that in our product for B, right, we don't have an alcohol group, but we have a carboxylic acid group here. So what is it going to do when we have SOCl2? It's going to turn that acid group into an acid chloride group. So we're going to end up with the product of that, right? Our OH is basically going to be replaced with a chloride. So now we have an acid chloride group. And the reason we want to form acid chloride groups is because they're the most reactive carboxylic acid derivatives. Why are they the most reactive? Chlorine is inductive. It's a halogen. It's going to draw electron density away from the carbon, and that makes the carbonyl carbon even more electrophilic. It's already electrophilic because it's connected to an oxygen, but because of this chlorine, it's going to be even more electrophilic and thus way more reactive. So this is a reactive, the most reactive carboxy acid derivative. So we can see that that's why we want to make it a chlorine, because maybe in our synthesis we're going to have something react with that carbonyl carbon. So that should give us sort of an idea for the future. So let's just write out the structures of A to C once again. For A, we have our structure looking like this, OH and our carboxy acid group. For B, this is A. For B, we have our structure with our ethylated oxygen, right? So we have O-ethyl, and then we have our carboxy acid group. And for C, we have our O-ethyl, but now we have an acid chloride group instead. So these should all be like pretty simple reactions. You should be comfortable with these reactions. So now let's look at the next part, right? I'm going to erase some of this, but let's look at the next part. We're looking at, basically, this is more steps in the synthesis of the active substance in Viagra. So the first step, we have this sort of pyrazole derivative, right? And we have our reagent being methyl iodide. So again, right, as we had ethyl iodide, with methyl iodide, it's really similar. It's going to act as an electrophile. Iodine is a leaving group. Iodide is a leaving group. So we're going to have a nucleophile-electrophile interaction here. So now we got to look at where are the nucleophilic sites in our starting substance, right? We look what has electron density. Oxygens can have electron density, but oxygens are less nucleophilic than nitrogens because oxygens are more electronegative. Because they're more electronegative, they're going to hog their electrons more, not going to be as willing to give them up and form a bond. So we've got to look at our nitrogens as our nucleophilic sites. So this is what we want to look at for what's going to attack our methyl iodide. So we have two options. We can either use both of these nitrogens have lone pairs. They're implicit. We can either use the right nitrogen. But if we methylate this right nitrogen, right, if we do something like that, we see we have a formal charge, right? We would have a plus charge on this nitrogen. But if we have a plus charge, that's sort of, we want to not have a charged substance, right? Because generally we're not going to isolate something that's charged. We're going to isolate something that's neutral. So we want to end with something that's neutral. So maybe the right nitrogen was not what we want to use, right? Let's see what happens if we look at the left nitrogen. So if we methylate the left nitrogen, right, we have this sort of reaction that goes on, and we add a methyl group. What can happen now, right? We have an iodide. So this iodide can regenerate aromaticity. It can relieve this positive charge and regenerate aromaticity, right? Because we need that lone pair on the nitrogen for this compound to be aromatic. So how can we do that? We can regenerate aromaticity by deprotonating this nitrogen because there was that free proton. So at the end of the day, right, we methylate the nitrogen and we have aromaticity back and there's no formal charges. That seems like the more plausible pathway, right? So basically, with the left nitrogen, we're going to methylate that, and then we're going to deprotonate that with our iodide, and that's regenerating aromaticity. And also another way to confirm this is we look at our final product, right? We look at our product here, not our final product, but the second to last step. And we look at where the methyl group comes off of, and you can see this looks like our pyrazole sort of part of it, right? That looks really similar with our nitrogens connected, two nitrogens connected to each other in the ring. So you can see that our left nitrogen is the one that's methylated. Our right nitrogen does not have the methyl group. That's another way to confirm your suspicions, but that should confirm that our left nitrogen is the one being methylated. So let's draw this out. So if I draw D, right, let me draw it here. We're going to have something that looks like, sorry if this takes a little bit, we're going to have an O-ethyl, right? And then we have our nitrogen methylated. Now, connect this to our other nitrogen. And here we have a propyl group. So I'm not going to draw all the carbons, I'm just going to abbreviate. Okay, so this is what our D should look like, right? Now, what is our next step? Our next step, we're adding NaOH and water. So we're basically doing some sort of base hydrolysis, right? That should give us a clue. We have NaOH and water, so we might be doing a base hydrolysis. And we also have a workup of H+, so this might be an acidic workup, right? So what can we hydrolyze, right? So we should look at our compound and we look at our functional groups in the compound, and we can see that there's an ester. This is an ester. And we should know that when we have base hydrolysis, we can have base hydrolysis of esters. And this is called saponification when we do base hydrolysis of esters. Saponification. So what does that do, right? When we hydrolyze our ester, we get a carboxylate group. So this is what we get basically at the end of the day. And you should be familiar with this reaction. It's sort of like the reverse of, it's like Fischer esterification, the reverse of that, but instead of acidic catalyzing, instead of acid catalyst, we have a base catalyst. So this reaction you should be familiar with, and if you're not, you should look up saponification. But this is what we're going to get when we do base hydrolysis. We're going to get this carboxylate group instead of our ester group. Then we have acidic workup. So again, what is acidic workup? We're just protonating everything that we've deprotonated. So we're going to protonate this carboxylic acid group, and we're going to reform the carboxylic acid. Now this is our E, so let's look at our next step. With our next step, we have this sort of HNO3, so we have nitric acid and sulfuric acid. So let me copy this over, and we should know what nitric acid, and we should be familiar with these reagents, right? Basically, what exactly do those reagents do? Nitric acid and sulfuric acid, you might have seen those reagents when we talk about nitration, right? When we talk about nitration of benzene or something like that. Nitration of benzene, for example, is when we use these reagents and we get a nitro group on benzene. So we get something that looks like that. So in the same fashion, we might do nitration of, instead of a benzene ring, instead of specific benzene aromatic ring, we can use our pyrazole aromatic ring and do nitration on that, right? So what do we want to do? We want to look at our nucleophilic site, or our nucleophilic sites on our ring. So you can see that this lone pair is sort of contributing to the aromaticity of the ring, and we can do some delocalization of this lone pair to some resonance structures, and we'll see that there is a resonance structure where we have a negative charge on this carbon, on that left bottom left carbon. So if we draw this out properly, right, there's a resonance structure where we have a negative charge on that bottom left carbon. So this bottom left carbon is nucleophilic, right? And because of that, we can nitrate it, right? We can nitrate this because this is a nucleophile. When we have these HNO3 and H2SO4 reagents, what does this form, right? This forms NO2+, an NO2+ sort of ion. So this negative charge on that carbon can go and attack this NO2+, just like it does in nitration of benzene. This is a reaction you should be familiar with. We want to look at our nucleophilic sites, and that's the site that's going to attack. So what are we going to end with in the end? We're going to end with something that looks like this. We're just going to nitrate that left position. So we're going to have our same thing, but we're going to have an NO2 group right there. And that will be our answer for F. Now let's look at our next step, right? Our next step, again, we have SOCl2 as our reagent, so we should know automatically SOCl2, that's just going to replace our carboxylic acid and make it a acid chloride. So let's do that. That's an easy sort of step, right? We know that that's what's going to happen. So I'm just going to copy this over, and there we go. So we have our NO2 group, and this becomes a chloride, right? So this is our step 4. This is our G, our answer for G. Now we can see our next reagents are NH3 and water. So we have ammonia and water. What can an amine do, right? Notice that we just replaced our carboxy acid and made it an acid chloride. Why did we do that? We made it more reactive. So maybe this gives us a hint. We're making it more reactive because we're going to react with it, right? So what can an amine do, or ammonia in this case? It can replace the chlorine on the acid chloride. Again, this is a reaction that you should be familiar with. This is just nucleophilic attack at a carboxylic acid derivative. So what this is going to do is the amine is going to replace the chloride, and we're going to form basically an amide. So we're going to have NH2 there, and we're going to have something that looks like this, same as before, right? Everything exactly the same as before, except we replaced our chloride group with a NH2 group. And the reason we even made it a chloride group to begin with was for this exact reason, because we wanted to react with it. Because when we add the ammonia, we want it to replace, we want to form an amide there, right? If we just reacted with ammonia here, we wouldn't get as good yields. Why? Because this carboxylic acid is much more stable, is more stable than the amide itself, right? But when we replace this with the chlorine, we basically destabilized it. We made the carbon really electrophilic, and then it's going to react pretty easily, and we're going to form our amide product well, right? So this should be our H. Now let's look at our next step. Our next step, we have hydrogen and on palladium on carbon. So hydrogen is a reducing agent. So this is a really common reducing agent. And some places you might have seen this is to reduce an alkene to an alkane, or an alkyne to an alkane. You know, you might have reduced a triple bond to a single bond or something like that. But hydrogen can also just be a reducing agent in general. So what can there be a reduction of that's easy to reduce, right? We want to look at what's most probably going to be reduced. And automatically we see a nitro group, right? Nitro groups are not the most stable. So what's going to happen is our nitro group is going to be reduced to an amine group. We're going to have a reduction of the nitro group. So what do we get at the end? We just get this nitro group replaced with an amine. So we get our same thing as before, except now we have NH2 rather than NO2. And we have our amide just as before. So we just have a reduction step, basically. Our next step, so this is I, this is our I. And our next step, we see that our reagent now is C. Our reagent is the thing we formed in the previous, in our 1.1 question. And if we remember what C is our acid chloride that we formed here. This was C. So let me draw that again here. We have our O-ethyl, and we have our acid chloride. And remember again, acid chlorides are very, very reactive. So there's probably going to be a reaction where we replace the chlorine with something else, some nucleophile, right? So let's look at our nucleophilic sites on our compound I, right? Let's look at the nucleophilic sites. We have a bunch of nitrogens, right? Which nitrogens are going to be the most nucleophilic? We can see that these two nitrogens are probably not going to be as nucleophilic because they're in the aromatic ring. It's like if this left nitrogen used its electrons to be a nucleophile, it would have a positive charge, and we can't deprotonate it to relieve that positive charge like last time. So that's not a good idea. If this right nitrogen, again, it would have a positive charge, and we can't do anything about that, and it would lose aromaticity, right? So that's a problem. So let's look at our other nitrogens. With our amide nitrogen, right, we might think that could be a nucleophile, but this can, its electrons can be delocalized, right? And our amides have a really good resonance structure where the nitrogen donates its electrons, and with a positive formal charge on the nitrogen and a negative formal charge on the oxygen. So there's basically the nitrogen loses a little bit of its electron density, so it's not as strong of an electrophile or a nucleophile in an amide. But here we have an amine, which is a strong electrophile. While this can delocalize into the ring, it's not as delocalized as in an amide. So we're going to look at this amine, and we're going to say that this is the nucleophilic site that replaces the chloride group, right? So let's use this, and let's react that with our C. And C was, just as a reminder, it's this guy. So basically this amine is going to replace this chlorine, and we're going to have our final structure will look something like, if we draw this out, we're going to have our pyrazole ring. So let's draw our pyrazole ring, and like this with our propyl, and our amide group like that. And we're going to have our amine group be attached to now this structure, this C structure. So we're going to have something that looks like a little like this. So we have basically we connect these two structures together. That's basically what we end with here. And this is our J, right? This is our J. So you can see that we just basically figured out most of this problem, right? So now we found J, and you can see that the next steps are basically given to you. You have a cyclization and loss of water that forms this guy, and with a few more steps, you form the actual compound in Viagra. And you can see that the difference between this compound and the actual compound is this sort of sulfur group thing. So, which in a future question, it actually asks what reagents we need to go from this compound to the actual compound. So let's not jump ahead really quick, but in general, we just solved all the structures that we needed for question 1.2. So we've just given the structures of D through J. So hopefully this wasn't too bad. All of these reactions should have been you should have known of them, right? They shouldn't have been really obscure reactions. You should know things like saponification. You should know base hydrolysis. You should know nitration. You should know the idea of replacing groups on a carboxylic acid derivative. You should know that hydrogen is a reducing agent. And like all of these should have been sort of common reactions. It was just more, how do you put all of this together, and because they don't really give you intermediates, right? You're given the first compound and you're given the last compound, and you sort of have to know what you're doing, right? They don't give you any hints in between. So it's basically making sure you're doing it correctly throughout, right? And keeping on checking your work. So let's look at 1.3. And I just said, like, we're trying to, the last question will ask us about the reagents we need to get from this second to last thing to the actual compound. So that's what 1.3 is asking. Suggest reagents for the final transformation required to form the active compound. More steps may be required. So you can see we have our second to last compound here, and we want to look at the differences between this and the actual compound. And as I just said, right, we have this sulfur group. That's the only difference, right? We have all of this is present. Sorry, all of this is basically what this compound is, except now we have this sulfur group that's para to our O-ethyl group. So our sulfur group needs to be attached here, basically. So what sort of common groups do we know that have sulfur in it that we can do with a aromatic ring? We should know of sulfonation, right? We should know of this reaction with benzene. If we have a benzene ring and we add fuming H2SO4, we should get something like this, right? With our sulfur, our HSO3 basically attached to our benzene ring. And this looks really similar, sort of, right? Pretty similar to the same sort of backbone as the thing we add in the actual question, right? So how about we try first doing a sulfonation step? So let's do that. We have this structure, right? So if we do a sulfonation step, I'm going to draw directly on it. We're going to get something that looks like that, right? And why do we attach it para to that, to the O-ethyl group? Well, first, that's what's in our product. Second, our O-ethyl group is going to delocalize electrons, right? It's a ortho-para director because it's an electron donating group. And that you should know from basic organic chemistry. So now we basically, what we want to do is replace this OH group with this sort of amine structure group, right? That's our goal, is to replace that OH group with an amine group. And we actually did that many times in this question, but not the same question, but we did the whole idea of replacing an OH group with an amine, or replacing an OH group with an NH2 group, or something like that. If you remember, right, when we went from F to G to H, when we went from F to G, we took an carboxylic acid and made it a acid chloride, and then we added ammonia or some amine and made this, converted this chloride group to an NH2 group. So basically the entire process went from an OH group to an NH2 group. We made it a chloride group so that we could make it an NH2 group because the chloride group is the most unstable, it's the most reactive, right? So that's exactly what we want to, our idea we want to have for 1.3. We want to convert this OH group into a NH or some sort of amine group. So let's first make it a chloride group. And how can we do that? We use SOCl2. So first we want to do our H2SO4 fuming, right? This is going to add this sulfur sort of group to it, our HSO3 group to the benzene ring, to the aromatic ring. Then we want to apply our SOCl2. And what is that going to do? That's going to take our OH group and make it a chlorine. And the final thing we want to do is replace that chlorine with our amine. And what amine group specifically do we need? We need an amine group that's going to make the final product have this sort of structure. So the amine group we want to use is going to look like this, right? It's going to look like that. We want this nitrogen is going to attack and replace that chlorine, and there's going to be a deprotonation of this nitrogen as well. Like if we look at this, when we have our NH3, right, when that reacted with our acid chloride, we ended with NH2. So we have a one less hydrogen in our product, right? And that's the same exact thing as with this last step. We have no hydrogens when we look at our actual product. That means we need one hydrogen for our deprotonation step, right, for our reagent. So these are the 3 steps I would take to make the final product from our second to last product in this synthesis question. So hopefully this all made a little bit of sense, this walkthrough of this organic question. I hope it was useful. I hope it was informative. Thank you guys so much for watching, and I'll see you in the next one.